what we want to do right now is we just want to tell whether or not a function is continuous or not, and we want to show it, okay? So if you have your notes, there were three main things that you had to do in order to show that a function is continuous, okay? So there are three things that have to happen. The first thing that has to happen for you to show that a function is continuous is you have to show that the function exists at the point. Right, because it doesn't matter what kind of line you have, okay, on a graph. If you get to, a certain point and you want the function to be continuous at A, but when you get to A, there's nothing there, right? Whether it be because there's a vertical asymptote or because there's a hole like with the green line or whatever it may be. If there's nothing there, it will be impossible for the function to be continuous. Definition of a continuous function is that you can draw it without picking up your pencil. So if you're talking about the point A and you want to show that it's continuous there, well, you want it to be continuous there rather. When you get there, if there's nothing there, it's quite obviously not continuous at that point, right? So the first step you have to take is you have to show that the function actually exists at the point, right? Okay, now the next thing that we need to do, does anybody remember? Exists, okay? So the limit as x approaches whatever point A, right? So I'm going to use the variable A. It could be any exist at A for the function, okay? And what this is going to do is this is going to eliminate the possibility for a jump discontinuity because part one requires that the limit actually exists, okay? Or sorry, that the function actually exists. So here's a function that exists. Here's a line coming out of it. But then I can do this. On the other side, I can go like that, right? And so this would pass part one because the function exists at the point A. It's right here where this closed circle is, right? But it would fail on step two because the limit wouldn't exist since the right hand aren't the same, right? So the limit from the left and the limit from the right are not equal. Therefore, this jump discontinuity. Okay, so that is option number two, right? Then the third thing we have to show is that the function is equal to the limit. And let me call this A, right? F of A. So the function at the point A has got to be equal to the limit at the point. Because we're trying to eliminate something like this from happening. So let me give you an example of what you're going to catch here. Okay? So I'm going to make up something that will pass, step one. It's not continuous. But there's a very difficult way, but there is a way you could get around, you could actually pass step one and step two without being continuous, and that's this. You could make the limit exist. So I'm going to make this my point A now, right? So I'm going to make the limit exist. So this limit exists, right, at A. Okay, I'll just put this right here and call it 2, right? So the limit would be 2. Does that make sense? Okay, so this thing right here has a limit of 2, so it passes step 2. That would be good for there. The limit exists. The function actually exists right here. So now the function exists, so that's part 1, right? The function exists where this dot is right here at the point A1, okay? And so it passes step 1 and it passes step 2, but is this function continuous? No, right? So this one has, a point that's outside of where the limit is, and that's what number 3 is going to catch, right? So part 3 will catch anything like that. Anything where there is a limit, but the point, isn't really fitting in where the limit is, then part 3 is going to catch that. So each of these specific steps are designed to catch a different type of discontinuity, right? So that's all we're going for whenever function exists at the point, the limit exists at the point, and then the function where the function actually is and where the limit is continuous at a point. Okay, so we're going to use some examples from the worksheet that you guys have, and we're going to just look at some different ones, and we're going to number 19, okay? So if you look at number 19, it says this. F of x is equal to 3 minus x when x is less than 2, and x divided by 2 plus 1 anytime that our x value is greater than 2. Okay, so we have a piecewise function here. And all that's happening is with this piecewise function, what we're saying is, we're using 3 minus x for all the x values that are less than 2, and x divided by 2 plus 1 for all the x values that are greater than 2. And so now we want to show that it's either show that this function is continuous or that it's not continuous. Okay? And so what we want to do is we just want to start with step number 1, right? What is the first thing that we're trying to show? Okay, and we're talking about, let me make sure I specify this. We're actually wanting to show that the function exists at x equal 2, okay? So this is the point that we want. So at x equals 2, we want to find out where the function is. So we actually want to find f of 2, right? We want to know where the function is when our x value that out. Yeah, we take the 2 and we just plug it into the proper equation. Equation or the bottom equation? Both right now. And the reason why is because Landon, it doesn't mean where we're coming from. F of 2 wants to know where we actually. So we happen when we get to 2. So when it's equal to 2, what's going on? Well, where would we put that? You're exactly right. We cannot do it, right? Because this top one is only for numbers that are less than 2. This bottom one is only for numbers that are bigger than 2. Well, the number that we have is not less than 2, and it's not bigger than 2. It is 2. Exactly right. Because this thing failed on. Right? The function can't be continuous there. So since we failed on step 1, we're just for f of x is not continuous at x equals 2. Right? Nice and simple. Okay, so that one failed on step 1. Let's do 21. 21 says this, f of x is equal to 1 over x minus 1 when x is less than 1, and x cubed minus 2x plus 5 anytime x is greater than or equal to 1. Step 1, and let me make sure I specify this again. We're trying to show that this function either does or does not exist at x equals 1. First thing we need to do is actually find f of 1, right? Very good. That I use if x is greater than or equal to the 1. So be equal going to plug in. So this will be 1 cubed minus 2 times 1 plus 5. It out. What are we going to get? 4. Very good. Okay, so this thing is 4. Okay, so part 2 is we want to show that the limit exists. But remember, in order for a limit to exist, what really has to happen? Yeah, it has to approach the same point from the left and from the right. So now we're actually going to take the limit from both sides. We're going to take the limit as x approaches 1 from the left of this function, and we're going to take the limit as x approaches 1 from the right of the function. Numbers that are to the left of 1, on a number line, how do they compare to 1? They're less than 1, right? So if we're talking right now about numbers that are less than 1, should we use the top function or the bottom function? The top one, right? Okay, and what we want to do is we actually would like to plug the 1 in. Okay, if at all possible, we want to plug the 1 in. But can we do that in this case? No, because if we plug the 1 in on bottom right here, 1 minus 1 is going to make a 0 on bottom. So what we're going to need to do is analyze this limit just like we would with any other limit, right? We're talking about numbers to the left of 1. So what's an example of a number to the left of 1? Yeah, 0.99999 repeating, okay? So if we take 0.999 repeating, right, and we plug it in there, don't let me repeat it, because then it is 1. That's another mathematical mind-blowing idea that we can talk about some other time. Make it negative, and then infinity, right? So we're going to end up with negative infinity. Now the second limit is a little bit easier. Right. So which one would we want to use in that case? It will use the bottom function because it's for x values that are greater than 1 or to the right of 1, right? You know, f of 1, we took 1 and plugged it in and got out 4. What does that mean for our limit? The limit as x approaches 1 of the function. That's exactly right. That limit does not exist since the left and right hand limits are different from one another. Therefore, because the limit does not exist, since the limit does not exist, the function is not continuous. And then I want to specify, because it's not that the function is just not continuous in place. The function is just not continuous at x equals 1, right? That's the point that we were actually talking about. So we've shown that the function is not continuous at the x value 1, right? So it's not continuous at x equals 1. All right, let's jump back up and do number 20. Okay. Okay, so here's our function. If x is equal to 2 and x divided by 2 if x is greater than 2. Okay, so step 1, let me make sure I specify again, is that we're worried about, the point x equals 2. We want to show that the function either is. The first thing we're worried about is the function, at the point. What do we get when we're at 2? 2. Very good. And we're just using this middle piece, right? Because it tells us that when x is 2, we go to 2, right? And remember, if we want the limit, we got to talk about it from the left, and then we have to talk from the right. So if we're talking about the numbers from the left, okay, things on the left of 2, then that means we should use. We're going to use this one, 3 minus x, because it's for values that are less than 2 or to the left of 2, right? So we want to take that 2 and just plug it in is the easiest thing to do. And so 3 minus 2 up here, once we plug 1. Then on the right-hand side, if we're talking about numbers that are to the right of 2 or bigger than 2, then we want to use this one because, x values that are bigger than 2, we're supposed to use. I'm using that one right there, and I'm going to get 2 divided by 2, which is 1. Okay, so we can say the limit as x approaches 2 of this function is going to be 1, right? Because the left-hand limit and the right-hand limit match. Limit actually needs to be equal to where the function actually is, right? So the limit needs to be where the function is. Well, we got a problem, right? The function is actually at 2 while the limit approaches 1. So this is not exactly what this graph would look like, but in general, this is what's happening. Okay, at x equals 2, there is a limit at 1. It exists up here at 2. Okay, and so because we have a limit at 1, but there's a hole in it, and the function actually exists up here at 2, this thing is not continuous. And so I'm going to say that I'm going to just put a little mathematical notation, and what I'm going to say is that f of 2, so the function at 2, is not equal to the limit as x approaches 2 of the function. And for that reason, or thus here, thus the function, or let me not call it the function, it's easier just to write f of x, right? Thus, f of x is not continuous. At the point x equals 2. Yeah, you want to get good at writing in a format like this. So you can say it really easily, right? Because you could write out the function and the limit were not equal to one another, but the function and the limit were not equal to one another. Well, look how much longer that took than to just say it mathematically, right? So we want to. Okay. Right. If you say, if you use the two words, or like kind of interchangeably, the word and the phrase, not continuous, or you say it is discontinuous, You may want to say that it has a discontinuity, right? Is another way you could say it, but all of those things are the same. Yeah. No, we're just talking about it at one point. If you say it is here, so that they don't think we're talking about the whole time, right? So that, whenever we put this down, we're all right, let's look at number 40. I'm going to jump way over to number 40, and we'll talk about it. Right? That's the big idea here, is that we need to show. So we got to provide a simple mathematical. It's not a really rigorous proof. It's a pretty simple mathematical proof, just that this thing actually is, that the function actually exists at 1. Where is the function at 1? It's right, because when x is 1, we just use 2. When x is 1, we use 2. So f limit as x approaches 1. Now I could let me stop right here for just a second and if we're coming from the left, which function would I use? The top one, because it's when we're not at 1, right? And if I'm coming top one, because we use it anytime we're a little bit special compared to the other one right here, when x was greater than 2. But when x was on the other side of 2, it was less than 2, we had to use this top one up here. Approaches 1 in general for x squared minus 1 over x minus 1, right? So instead of breaking it apart, I'm just going to use that 1 because we would use the same 1 for the left hand and for the right hand, right? So we can just talk about it all in one piece instead of having to break it in 2. Now remember, our first option with a limit is always to plug in, right? But that won't on bottom. But notice we'll also get a 0 on top. And remember that 0 over 0, as I'm sure you already know, the top is a difference of squares. So it's going to factor into x minus 1, x plus 1. And the bottom we can leave alone as x minus 1. And it's going to cancel. And so now we're talking about the limit as x approaches 1 of x plus 1 is all that's left. And we get 2. Yeah, and the last thing is that we need where the function is at 1 and the limit at 1 to be equal to one another. And you can see that they're both 2, right? So instead of writing out the function was 2, and I'm just going to do it very simply. The function, f of 1, was equal to the limit as x approaches 1 of the function, and equal to 2. Therefore, f of x is continuous. Yeah. We're just trying to show that the function and the limit are at the same spot. And we didn't prove that this thing is continuous everywhere, right? We showed that this thing was continuous at 1. So let's not get ourselves carried away. It may be continuous everywhere else, but we haven't shown that. So all we're trying to do right now is just say that the function is continuous at the point x equals 1. This is a specific instance that we're talking about. Okay? All right, so you'll have some problems like that will be on your quiz tomorrow. Well, actually, the quiz may be on Friday. The process